In this video, I'll take you through an AP style problem involving area and volume. You can see we're going to be given a region R bounded by a curve, a line, and the y-axis. Let's take a look at the types of questions we'll be asked. We're going to be asked to find the area of R. We're going to be looking for an integral expression for the volume of the solid when it's rotated, indicating we'll need the washer method. And for part C, we're given R as the base of a solid with cross sections perpendicular to the y-axis, indicating to me that we're going to have to put things in terms of y. So let's go ahead and take a closer look, and we'll solve for the area of R first. And we'll note if I take a slice perpendicular to the x-axis, we have a thickness of dx. So everything will be in terms of x. So I see my upper bound here is 8, and we'll be coming from 0. And we have an upper curve of y equals 9, and our lower curve is 3 root x. And we know to find area, it's across our bounds, and it'll always be the upper curve minus the lower curve, regardless of where it is. If it was in terms of y, we would have right minus left. So let's go ahead and write that integral down. So we're going to be integrating from 0 to 8 because our slices will be going across that region. Our upper curve is 9. Our lower curve is 3 root x plus 1. If there was more terms, we'd want to put that all in parentheses, but we just have the one term, so we are safe doing this. Now we can go ahead and integrate. It's fairly straightforward. Integrating 9 will give us 9x minus 3. And then we're multiplying by root x plus 1. You'll remember that root x plus 1 is simply x plus 1 to the 1/2. And the inside function, its derivative is 1, so it'll have no real impacts. We won't need the chain rule or anything like that for u substitution. And we can simply go ahead and integrate that, and we'll have x plus 1 to the 3/2. And then we'll divide by 3/2, which is multiplying by 2/3, and conveniently those 3's cancel, and we'll be evaluating that from 0 to 8. Substituting in, we get 9 times 8 minus 2 times 8 plus 1, so we'll just go ahead and write down 9 to the 3/2. And we're going to be subtracting the entire quantity, so make sure we use parentheses. 9 times 0 is 0, minus 2 times 0 plus 1, which is 1 to the 3/2. Some people do make the mistake of just ignoring the 0, but sometimes you are left with a non-zero term, so be aware of that. And if you're taking the AP exam, this is as far as you need to go. However, we will continue and simplify just to be satisfied with the final answer. We have 72 minus 9 to the 3/2 means the square root of 9 to the 3rd power, so 3 to the 3rd is 27. So we'll have 2 times 27 minus, inside here we'll have a minus 2 or a negative 2, so that'll end up being plus 2. And this will give us a final answer of 20. And you will notice there are no units here because we weren't given any units, so we are all set. In part B, we're told that this region R is going to be revolved about the horizontal line y equals 10. So let's go ahead and put that in. And again, it doesn't have to be to scale as long as we understand where everything is. And let's go ahead and take a slice. If we're slicing perpendicular to the axis of rotation, which in our case is dx here, it means we will be using washers. If it was parallel to the axis of rotation, we would be doing shells. So I remember parallel for shells, but we're just going to look at the washer method here. And if we recognize that we do have washers here, the only thing we need to identify is the inner radius and the outer radius. So the inner radius is from the axis of rotation to our first curve. The outer radius is the axis of rotation to our second curve. And then we know that this entire length here from the x-axis is 10. And coming up here, we have the distance to our first curve and the distance to our second curve. So we just have to be able to identify the outer radius and inner radius. So this is, we'll say, r sub o, r sub I. And we should know that the washer method, it's simply pi, the integral from our bounds, a to b, which again in our case, since it's dx, is still 0 to 8, of our outer radius squared minus our inner radius squared. And those are the notations I use for outer and inner, just for clarification. So let's go ahead and identify what our outer radius is. our outer radius is just that distance right there. So since the entire distance is 10, and this is our curve y, or 3 root x plus 1, it is going to be that distance 10 and then minus that distance y going up. So it's just going to be 10 minus 3 root x plus 1. And for all these washer problems, whenever the horizontal line is above the curve, it's going to be that value minus. If it's below the curve, it's going to be that value plus. And then our inner radius, we can see, is still the idea of 10 all the way down, and then we're returning back up to 9, so it's 10 minus 9, or you can simply see that that distance is constant. It is always 1. So I'm just going to write 10 minus 9 in case it was not constant, and in this case it is, then we'll say it's 1. And if we wanted to see what this actually looked like when it was rotated about, you don't need to, but some people do like to see that at first. We would have, here's a picture of half the washer coming around, and we would have that. So that shows us that it's washers, but we don't need a 3D picture to solve these. Now we can simply substitute into the formula and solve. And remember, we only have to set up the integral, so we don't have to actually get a final answer. So our limits of integration are 0 to 8 because our slices in terms of x are from 0 to 8 right there. And our outer radius, make sure we use parentheses, is 10 minus 3 root x plus 1. And then don't forget that squared, minus, and I'm just going to put this in parentheses regardless, 1 squared, and then I'll close it off with a dx. And we've successfully written our integral for the washer method. In our last problem, we're told that R is the base of a solid where the cross-sections perpendicular to y-axis are semicircles. So we are perpendicular to the y-axis, so let me go ahead and do a slice. And we could derive this, but for semicircles it is a known formula. You can go back and look at my cross-section video for that if you'd like to. So the formula for semicircles is always going to be pi over 8, the integral across our bounds, and then whatever the side length is, squared. So I'm just going to write side squared, and that's the only thing that we're going to have to solve for. And since we're perpendicular to the y-axis, our thickness is dy, and we can see that right there, it's dy. So again, we don't need a picture of semicircles. If we were to take a look at that slice, basically we'd be solving for what the area of that face is. And again, we just have to find the side length. And our side length here, since we're going horizontal, is going to be the right curve minus the left. The left curve is the y-axis, so that's 0. So the only thing we need to look at is this distance x. So we're given this in terms of y, so we just have to go ahead and solve for that. So let's do that right here. We have y equals 3 root x plus 1. We'll simply divide by 3. Square both sides, give ourselves a little space here. So we get y squared over 9 equaling x plus 1. So that tells us that x is equal to y squared over 9 minus 1. And that's going to be our side length, as you can see right here. So we're just going to use our formula we have written down, and our final answer is just going to be pi over 8. The integral from now, our lower limit of integration, if you recall, was 3 up to 9. So now we're using that 3 to 9. Our side length is y squared over 9 minus 1. That entire quantity squared dy. And we're done.